discovered that there are excited states in atoms. It was first used by Franck Hertz in 1914 to prove the prediction of quantum theory that electrons occupy only discrete quantized energy states. This supports the Bohr model of an atom, where electrons orbit a small dense nucleus at a specific energy state. Isn't that right, Reese?
It is, Rob. Right. The Franck Hertz experiment aims to find the excitation energy between the ground state and the first excited state in neon vapour.
Cracking.
This is obtained by exciting the atoms by changing the voltages of the different plates within the neon tube. The plates then change the kinetic energy of the electrons. This helps to highlight the interactions of the electrons and the atoms.
Smashing. See you in a minute.
Can I swoop? So what's the theory?
Well, this all happens with fermionic emission from a cathode, which then uses a positive potential which accelerates the atoms to higher and higher energies. During this, the electrons will be in a neon tube. The electrons then inelastically collide with the neon atoms at a specific energy, causing the atoms to excite. The electrons doing this lose energy due to the inelastic collision. Visible light can be viewed due to the de-excitation of the atoms which emit the photons within the visible light region.
So,
What equations do we use?
well, Rob. This equation calculates the standard deviation of the data, where sigma is the standard deviation, xi is each value of the data, xm is the mean of the data, and n is the number of data points. The second equation calculates the standard error, where delta z is the standard error, sigma is the standard deviation, and n is the number of data points. This third equation finds the voltage per division, where delta z is the change in time during the voltage change, d is the voltage per division, and delta v is the change in voltage between 0 and 99 volts. This fourth equation finds the general error propagation. Z is the error, f is the chosen function, delta x is the error of variable 1, delta y is the error of variable 2, x is variable 1, a chosen data of variable 1, and y is a chosen data of variable 2. This final equation gives excitation energy, where U1 is the accelerating plate voltage of the trials of the graph, explained better later in this video presentation. N is the order in integers 0, 1, 2, 3, etc. And E subscript EX is the excitation energy. But how do we do it? So this is a photo showing the experiment all set up. With the Franck Hertz control unit. The control unit was connected to the neon tube with a 5-pin cable from the 5-pin adapter to the bottom adapter on the neon tube, which controls the different voltages of the tube. The BNC cable was attached from the current to the top input. Finally, the banana connections were attached to more BNC cables and attached to the output of the control unit on the UI and UU slots, then inserted into different channels of the oscilloscope, the X and Y channels.
So in order to use the oscilloscope, set it to the XY mode, which plots the coordinates on the screen. Do it by pressing the horizontal button and changing the setting to XY. A dot should appear on screen, press start on the control unit. This performs a voltage sweep from 0 volts with an error of 0.05 plus or minus to 99.90 with the same error, 0.05 volts. While it's sweeping, the oscilloscope should be paused so the waves could be easily seen, and the time distance can be measured with the cursor for more precision. Sweep.
So, this is a diagram showing the plates within the cathode tube and the inner workings, also showing the corresponding voltages that were set out earlier in the methodology. UH is the potential difference over filament for heating. This filament was used for emitting electrons by applying energy to it with heat via voltage. U3 is the potential difference between the filament and first electrode grid. This is the potential difference needed to draw the electron away from the filament, as due to the forces when the electron leaves and it's naturally pulled back, we need an anode pulling it away. U1 is a potential difference between 0 and 99 volts. This steadily increases, increasing the kinetic energy of the electrons and pulling it to the second electrode grid. U2, finally, is the potential difference between the electrode grid and the counter-electrode grid. This is the decelerating voltage to filter out the low energy electrons, otherwise there will not be a clear trail where the electrons would have lost kinetic energy interacting with the neon and would have got through anyway. This electrode grid filters out into electrons only going in the I direction. As previously mentioned, a voltage sweep is completed. This will produce a graph as shown on the screen now. The time difference between trials are measured using the cursor functions on the oscilloscope. On the screen it can be seen that there are two graphs shown. One with the peaks and the troughs as previously mentioned and shown on screen, and one with a steady gradient. The one with the steady gradient is the voltage sweep, increasing from 0 to 99 volts. This can be used to see where you should measure from and to on the troughs. It also can be used to work out how many volts there are per division in the time.
Oh, hang on, wait. What about the results and the analysis?
Well, stay tuned.
Right. Let's discuss the experiment. Well, you are ready?
No.
So, now that we've performed the experiment, shall we see some results on screen?
Well, they should be there for the power of editing.
Power of editing. Is there any anomalies with any of those results?
Well, kind of, yeah. We've got a 10 electron volts, which doesn't really make sense, and we can't work out why that's there. It's to the literature values, it's not right. The other two results we have fit, but within the margin of error, they're not correct. So something has gone wrong. So how could it be improved?
Well, I'd say use technology. I mean, we've got the oscilloscope, but I think if we used some sort of computing program which allowed us to measure each point more accurately, I think if we did it again and used that.
Well, yeah, we were arbitrarily picking
the trials of the graph. Like, it wasn't ever exact. It wasn't one single pixel that was at the bottom.
No.
So the results did vary in that way.
Yeah.
But I think with the 10 electron volts, there's something completely systematically gone wrong, because every time we did it, it was there. So we should have started again with new equipment once we realised that it was going wrong.
Yeah, I suppose that works.
What about the conclusion, Rob? Rob?
So to conclude, the basic aim of this experiment was to find the activation energy using the Franck Hertz setup. Yeah, good that. The objective was to obtain the activation energy and to confirm the Bohr model of an atom. Of course, this was done by applying a voltage to the Franck Hertz neon tube and exciting the electrons. This would then give off some sort of kinetic energy, which then could be measured on the oscilloscope. We could then use the troughs of the oscilloscope to find the activation energy. The results of this should be shown on screen now. Editing skills, majesty. The only suggestion I would have to improve the experiment is perhaps use a more advanced oscilloscope, or maybe a computer to measure more accurately the trough, and to see what happens if we tilt the grid inside of the tube at an angle and see how that would affect our result.